Welcome back to the Physics Almanac. In this video, I'm going to be deriving Kepler's second law of planetary motion using Newton's laws of motion and his law of gravity. I've already derived the first law in the previous two videos of this series, so if you're interested in that derivation, you can check out those videos. Otherwise, let's move on to Kepler's second law. I've rated the physics level in this video as easiest. First things first, let's remind ourselves what is Kepler's second law of planetary motion. It states that a line connecting a planet and the sun sweeps out equal areas and equal times. That means that if the planet moves along its orbit over some time interval delta t, if you take a line connecting the planet to the sun, the area swept out by that line will be the same no matter where in the orbit the planet is, so long as the time interval is the same. So if the planet is over here and it's displaced over the same time interval, the area swept out will be the same. Now, don't get the wrong idea here. I drew this figure in a symmetric way, but that's actually not important. The starting point could be anywhere along the orbit, and as long as the time interval is the same, the area swept out will be the same. Now, if you saw my video on Kepler's three laws, you might recall that he came up with this second law using a series of false assumptions. And yet, when those false assumptions were combined, it happened to still give the correct answer. So let's start off by going over Kepler's logic in coming up with this law. His first law of planetary motion says that planetary orbits are ellipses with the sun at a focus. But that's not enough to predict the motion of the planet. You need to know, how do the planets move along that ellipse? And that's where the second law comes in. And Kepler made a series of assumptions, incorrect assumptions, in how planets should move. First, he assumed that in order to maintain motion, a force must be continuously applied. This is in line with the reasoning of Aristotelian physics, that the natural state of things is to be at rest, and so in order to keep them in motion, a continuous force must be applied. As a result, he reasoned this force must be pushing the planet along its orbit. And since the force is what maintains motion, the force must be proportional to the velocity. Now, this is pre-Newton, so I don't know exactly what his definition of force is. I don't know if it's a vector, or if it's just a number, or if it even has a clear definition, according to Kepler. He then reasons correctly that the motion of the planet must have something to do with the proximity to the sun. And he reasons, well, if the sun's really far away, the planet probably doesn't know about the sun, so it should decrease with distance. And he guesses that the force should be inversely proportional to the distance to the sun. So r here is the distance between the sun and the planet, the length of this green line. He's now going to combine all these to come up with his second law. Let's say the planet is displaced by some amount delta s. And let's assume delta s is small and takes place over a small time interval delta t. And the line connecting the planet and the sun is now going to sweep out a small area, which I'm going to call delta A. Now, this is basically a little triangle. It's got a base delta S and a height r, the distance between the sun and the planet. And the area of a triangle is 1/2 base times height, so that's 1/2 delta S times r. Now, delta S is just the displacement, so that's equal to velocity times time. So the area must be 1/2 velocity times time times r. Now, according to his view of physics, the velocity is proportional to the force. So we can now substitute that in for v to get that the area must be proportional to F times delta t times r. But he's guessed that the force is inversely proportional to the distance. Substituting that in for F, we find that the r's cancel, and so the area must be proportional to the time elapsed. Kepler then compared this result to his data and found that it matched. And there we have it, Kepler's second law. So now that we know how Kepler arrived at this law, let's see how we can get to it using Newton's laws instead. But first, if you're finding this video helpful so far, please take a quick second to like and subscribe, maybe share with a few friends, and if you'd like to support the channel, there'll be a link to my Ko-fi page at the end of the video. You can also find it in the video description. Okay, so first thing, we gotta erase all this because we know this is using incorrect reasoning. For one, force doesn't maintain motion, force changes motion. Quite literally, as Newton defined motion as momentum, and Newton's second law defines force as the time rate of change of momentum. Since force is changing the motion instead of maintaining it, it's not going to point along the planet's trajectory, but in the direction of the change in motion, which is towards the sun, according to Newton's law of gravitation. Also, since force is changing motion instead of maintaining it, it's not proportional to the velocity, but to the acceleration. And Kepler's final guess was along the right lines in reasoning, but it turns out the force of gravity is not inversely proportional to the distance, but to the distance squared. Now let's derive Kepler's second law using the correct physics. The area of this triangle doesn't change, it's still just the area of a triangle, it's 1/2 base times height, but the base is not actually delta S. The base is the component of delta S that's perpendicular to R. So this should actually be 1/2 delta S perpendicular times R. And almost certainly Kepler knew this, but planetary orbits, while they are ellipses, are almost perfect circles. This drawing I have here is highly exaggerated. No planet has an elliptical orbit anywhere as oval-shaped as this. In technical terms, we say, with such a large eccentricity. If you were actually to draw out planetary orbits in their correct proportions, you would struggle to notice that they were not perfect circles. In this diagram, the ellipses have the right shape, but they're not to scale relative to one another. So given that they're almost perfect circles, delta S perpendicular is pretty much delta S. And Kepler almost certainly knew this, but ignored this tiny inaccuracy. Consequently, this also means that delta S perpendicular is v perpendicular times delta t, meaning the component of the velocity that's perpendicular to the radius. Delta S perpendicular is the radius times the change in angle. And now I'm switching to ds and d phi, where phi is the angle subtended here, and d phi and ds are infinitesimal changes. We already had assumed that delta S, delta t, and delta a were small quantities, but now we've got Newton, we know calculus, so let's be a little more rigorous and use infinitesimal quantities. So our infinitesimal area, dA, will be 1/2 the radius times d phi times the radius. I'm now going to divide by the infinitesimal time interval dt to get the time rate of change of the area is 1/2 r squared d phi over dt. If you watched the previous video on Kepler's first law, you'll know that one thing that popped out of that derivation was that r squared d phi dt was a constant, which we called little l. And we found that that constant is the angular momentum divided by the mass, sometimes called the specific angular momentum. So dA over dt is equal to a constant. Therefore, any finite change in area is proportional to a finite change in time. And there we have it, Kepler's second law. If I look at the planet's displacement at a different point along its orbit, so long as the same time has elapsed, the area subtended by the line connecting the sun and the planet will be the same. And actually, it's quite easy to show that if the sun is not there and the planet's moving in a straight line because no forces are acted on it, this law also holds. Because we've just shown that Kepler's second law is just a consequence of conservation of angular momentum. And that's also conserved in absence of forces, when the object is moving in a straight line. What's astonishing is that the numerous physics mistakes Kepler made all happen to cancel out coincidentally in just the right way to still give a correct law of physics. By the way, while delta A and delta T are the same anywhere in the orbit, delta S is not. So the distance traveled along the orbit will not be the same for equal times at all places in the orbit. It's easy to see as a result of this law that the planet has to move faster when it's closer to the sun and slower when it's further away from the sun, in order to make sure that over the same time elapsed, the same area is swept out by the line connecting the planet and the sun. In the next video, I'll be using Newton's laws to derive Kepler's third law of planetary motion. So if you enjoyed this video and would like to see that derivation, please be sure to like and subscribe, hit the bell to be notified for the release of future videos. And if you feel so inclined and you'd like to support the channel, you can go to my Ko-fi page, or you can just leave a super thanks. It will be most appreciated. Thanks for watching, and I'll see you in the next one.